Hi, I'm Omalade Misaliu, and this is my report on bar magnets. The purpose of this experiment is to investigate how the magnetic field produced by small permanent bar magnets depends on distance and orientation. By measuring the magnetic field strength along the magnet axis and off-axis directions using a smartphone magnetometer, we aim to verify the theoretical distance dependence directed for a magnetic dipole. Additionally, we will compare experimental data to theoretical expressions derived from the Biot-Savart law and determine the magnetic moment of the bar magnet. The system in this experiment is the bar magnet, which produces a magnetic field due to the alignment of the magnetic dipoles within its material. The surroundings include the Earth's magnetic field, nearby non-magnetic materials, and the smartphone magnetometer. This lab investigated the magnetic field of a bar magnet and how its strength varies with distance. By measuring the x component of the magnetic field, Bx, at multiple distances r and analyzing the data through logarithmic linearization, the experiment verified that the magnetic field approximately follows an inverse parallel with distance. The slope of the graph was found to be negative 2.1998, confirming the expected dipole-like behavior. Using the linear Phys parameters, the magnetic dipole moment of the magnet was calculated to be 11.565. A closed-group Python model was then created to visualize the theoretical magnetic field distribution based on this experimental value. A bar magnet can be modeled as a magnetic dipole with a magnetic moment mu. The magnetic field at a point in space due to a dipole is given a general expression derived from Biot-Savart law. The experiment applies fundamental concepts of magnetism, specifically the magnetic fields produced by current loops and dipoles, to a real-world permanent magnet. The investigation demonstrates how the dipole approximation accurately models small bar magnets, the inverse cubic relationship between field strength and distance, and how vector components of magnetic fields can be measured and analyzed using modern smartphone sensors. Through careful alignment, compensation for Earth's magnetic field, and quantity-scale analysis, the lab connects theoretical magnetic field equations to the experimental observation. To proceed with this lab report, we must clarify assumptions. We must assume that atmospheric and environmental conditions are stable. Assume there are no additional magnetic or electric fields that could interfere with our measurements. Assume that Earth's magnetic field remains constant throughout the experiment. Assume that the bar magnet behaves as an ideal magnetic dipole. Assume that the bar magnet is small compared to the measurement distances. Experimental data were collected using a magnetic field sensor at several distances from the magnets R20, R70, 120, 170, and 220 units centimeter. For each position, 3 measurements were recorded. Average values for both distance r and bx in Tesla were calculated. This result showed that the magnetic field decreased rapidly as the distance increased, following the expected dipole trend. The logarithmic transformation of the data produced a linear relation with the equation, indicating a parallel dependence. Let's confirm that the field of the bar magnet approximates that of a magnetic dipole. Small deviations from the theoretical exponent of -3 were attributed to real-world imperfections in magnet and measurement precision. In the computational portion, the closed-script V Python environment was used to simulate and visualize the magnetic field using the experimental magnetic moment 11.565. A function was written to calculate the dipole magnetic field, as you can see in the photo to the side. Vectors were displayed along the magnet axis, perpendicular directions on a 45-degree axis offset. The resulting model showed the spatial orientation and relative magnitudes of the field. The computed magnetic field magnitude at 45 degrees was as shown, compared to the experimental value of as shown. Discrepancies were likely due to assumptions in dipole approximation and environmental factors. Overall, the simulation validated the experimental findings and effectively illustrated the magnetic field geometry. Recall earlier, we had listed several assumptions made in order to proceed with this analysis. These assumptions can be presented as sources of error. Thus, our total sources of error are assuming ideal atmospheric and environmental conditions, assuming no interference from external magnetic fields, assuming perfect alignment with the Earth's field, assuming the bar magnet behaves as an ideal dipole, assuming a constant magnetic moment, assuming the smartphone magnetometer is perfectly calibrated and linear, and human error. If the setup wasn't aligned with magnetic north, the Earth's magnetic field would mix with the magnet field. This would distort the BX readings, making the data less accurate and likely the slope deviates from the expected -3. 2 identical magnets stuck together would act like one stronger dipole with roughly twice the magnetic moment, so the field strength would about double and the distance dependence will stay the same.